looking at a more concrete example, or simpler one, we have an ideal spring. It has a potential energy of 1/2 kx squared. So it looks like this. If I find the force is minus the derivative of potential energy with respect to x. That means the force in here will be negative, the force in here will be positive. If I were to sketch it out, this is force versus x. You should remember that for a spring, this looked something like this. Force was proportional to negative x. Okay, so in here we get a force that's in the negative direction, in here we get a force that's the positive direction. That means if I had something sitting here, well, at that point it's at rest, so it's not going to go anywhere. But what if I brought it up here? It's at rest and it's at a zero force. Up here, I set it at rest. Oh, it's no longer a zero force. The force will push it towards this point where it was zero, where the force was zero. Of course, it'll pick up some momentum and roll back over here, but when it gets here, the force will push it again back to this point. And it'll be pushed back and forth, always staying near this position. So this is a place where it's in equilibrium. We set it there, the force on it is zero. It'll stay there. But not only is it in equilibrium, but if I move it a little to the right, it gets pushed back. If I move it a little to the left, it gets pushed back. Either direction that I push it, it gets pushed back towards the equilibrium point. And that's what we call a stable equilibrium. If you move it one way or the other, it gets pushed back to the equilibrium. All right. If we look here, we have another kind of equilibrium. If I place the dot here at the top, it's still in equilibrium. The force on it is zero. However, if I move a little bit to the right, suddenly now I've got a force that is also to the right, and it'll be pushed away from the equilibrium. If I move it a little bit to the left, there's a force on it to the left, and that will be pushed away from equilibrium. So in this situation, we've got an equilibrium, but we tend to be pushed away from the equilibrium. That's called an unstable equilibrium. So another kind of equilibrium, right over here, if I were to put a ball at that point, it's in equilibrium, there's no force on it, but if I move it a little to the right, that'll still be equilibrium. There will still be no force on it. If I move it a little to the left, that's still equilibrium, still no force on it. So in that situation, it has no tendency to move away from the equilibrium point, nor any tendency to move toward the equilibrium point. Net result, it's what we call a neutral equilibrium, neither stable nor unstable.